let's see if you remember something about even and odd functions. And if you don't, that's fine, because here we are to review it. So we're going to start off with a little rule for calculus. And this rule says that the integral from negative a to a of some function equals something if f is even, and it equals something else. Let's add a dx. Dx is important. If f is odd. And I'm not going to tell you what this is yet. We're going to have to explore and discover this together. Okay? So let's remember what even and odd functions are and then see if you can come up with the formula. So recall f is even if a negative on the inside doesn't matter. So negative on the inside is the same as no negative at all. And graphically, we can think about this as symmetric with respect to, that's my shorthand, WRT, with respect to the y-axis. And then we'll talk about what it means for something to be even. But first off, let's look at this graphically. Let's see this in action, okay? So some examples of even functions are x squared. That's one example. And then you can see that symmetry, right? Symmetric about the y-axis. Symmetric on either side of that vertical line. So what does that tell us about the area from, let's just think, -2 to 2? Well, since we have symmetry, there's something that's going on with the area as well. Let's look at another even function. What if we looked at the even function cosine of x? Again, it has that same symmetry. It will always have that same symmetry. And again, let's look from maybe -2 to 2. What can we say about the integral here? Now, again, integral is not just area. Integral is net signed area. So it's this positive area minus the negative area. What are you noticing about the area to the left and the area on the right? That's our first formula. If the function's even, well, then the function value on the right is the same as the function value on the left, which means the net signed area is going to be the same on both sides as well, right? This positive area is the same as this positive area. So instead of going from -2 to 2, we can just double this stuff on the right. So if f is even, we're just going to say this is double the integral from 0 to a of this function. So you still have to do an integral. But when your limit of integration is 0, we've already seen this. When your limit of integration is 0, a lot of times the area, the plugging in step is a lot nicer to calculate. So that's why this is useful. It can save us time if we recognize that something's an even function. All right. And then again, if something is odd, the formula is even nicer. Let's look at some examples of odd functions. X cubed. So on the left, it's just the negative version of what's on the right. Sine of x. On the left, it's just the negative version of what's on the right. Or the cubed root of x. How about that? Well, on the left, it's another odd function. On the left, it's just the negative version on the right. So if we're looking at the integral from -2 to 2, anytime we have positive area on one side, we're going to have the exact same negative area on the other. Oh, so this is really nice. So if we're looking at total area, yeah, we can't do that much. It just becomes basically the same as the even situation if it's total area. But if we're looking at the integral, if we're looking at the net signed area, we have what is one of my favorite calculus formulas. They always cancel out. All right, that's too big of a 0. But the point is it's a 0, and that's kind of nice, right? So that's a nice little formula that you can use in this section and the future if you recognize that the integrand, the function that we're integrating, is even or odd. And remember, we also need this. We need the limits of integration to be the same in the positive and negative direction, right? Because if we're going from -1 to 4, it doesn't help us as much. Although it actually still does help us in that case. If we're going from -1 to 4, you know the -1 to 1 part cancels out, and you can actually just go from 1 to 4. But that's what we're doing in this video. We'll do some problems, really cement this. And yeah, that's the section. That's the whole section. Just 2 examples, and that's 1.4. So example 4. Integrate the following. And show this rule holds. So we're going to find the integrals directly. We're going to find the integrals with the formula and see that they match up. Let's start with the messier one, the even one, because the odd one is really nice. Start with the even function, -2 to 2. So again, we have that -a to a format of 3x to the 8th minus 2. So first, let's evaluate it directly. And when we evaluate it directly, you can really see the calculus for why that formula holds. You're really going to be able to see where that 2 comes from when we do it directly. So first things first, just definite integral the regular old way. Not with the rule, not with the formula. Just find this the old-fashioned way by taking the antiderivative, add an exponent, and divide by the exponent. 3 divided by 9 is 1/3. Minus 2x, we'll be evaluating that at -2 and +2. We plug in +2, we get 1/3 times 2 to the 9th minus 2 times 2. And we subtract when we plug in -2, we'll get 1/3 times -2 to the 9th minus 2 times -2. We'll keep simplifying. 2 to the 9th is, I can do this. 2, 4, 8, 16, 32, 64, 128, 256, 512. We'll get 512 over 3. There's no way I'm making another mistake in my head, right? Minus, what does this become? -512 over 3 plus 4. Now, before you get excited and think it all cancels out, remember we have to distribute that negative. When we distribute that negative, this becomes a plus, this becomes a plus, and that becomes a minus, and you're going to notice that we have a positive 5/12 plus a 5/12. Now we have 2 of them. We have a -4 minus another -4. Hey, now we have 2 of them. You can really see that where that formula is coming from. So now we have 2 of them. It's 10/24 minus 8, which is 24/3. Oh, our answer is nice. When we write 8 as 24/3 and subtract it, we just get 1,000/3. All right. And we can do this again using the formula on the next page. Since it's an even function and it's got the right format, we know this is going to be double the integral from 0 to 2. Take a moment, pause the video, do the integral out this way, and make sure that you get the right answer. So when you do that, hopefully you got double. You still found the antiderivative, which is still 1/3 x to the 9th minus 2x. We're still evaluating, now we're evaluating from 0 to 2. The 2 is out in front of the whole thing. And we're going to get 1/3 times 2 to the 9th minus 2 times 2, just like we had before. But the other one just becomes 0 minus 0. And then again, just like before, this is going to become 5/12 minus 4. And when we double and combine like terms, we're going to get the exact same thing of 1,000/3. And we can check our answer, but we just showed that both of these are the same. We've shown that this rule holds for this problem. And again, if you were hypothetically a math professor who had been making a lot of arithmetic mistakes, you might check your answer on GeoGebra. get 2x to the 8th, 3x to the 8th, minus 2. Hypothetically, if you were one of those people that cared, that is 1,000 thirds, yes. 1,000 divided by 3. Beautiful. All right, so let's show that the other one holds. And this will be even quicker. This will be part B. Integral from negative pi to pi of negative 5 sine of x dx is an odd function because sine is odd. A negative just flips it upside down, still odd. And the 5 just stretches it out, increases the amplitude, still odd. Is an odd function. Let's say we knew it was odd. Boom. We know it's odd. We're already done because we have a symmetric interval that we're integrating over. Negative pi to positive pi. But let's say we didn't know that. Let's say we didn't have this rule and we had to do it the long way. This is what it would look like. And you can see all the fun. You get to see all the fun that the rule is saving you. You get to see the fun that the rule is stopping you from doing. I don't know. I don't know how to turn this into a good thing for you. So we need to find the antiderivative. Remember, the derivative of cosine is negative sine. Oh, so we're opposite. So the antiderivative of sine is negative cosine. When we take the antiderivative, we get 5 cosine of x. And especially with these trig functions, I'd really recommend you check, right? When you take the antiderivative, you can check by taking the derivative, and hopefully you can go backwards, right? If we take the derivative of 5 cosine of x, we should get negative 5 sine of x, which we do. So anytime you're taking a derivative, it's really good practice, especially on like quizzes and tests, to make sure that you can go backwards. Especially when we get to like more complicated integration rules like substitutions, trig integration, integration by parts and all that stuff. In the meantime, we can just go through this normally. Plug in pi, we get 5 cosine of pi. Minus when we plug in negative pi. Remember, cosine is just the x-coordinate on the unit circle. But pi, well, pi and negative pi, first off, are the same x-coordinate on the unit circle. And the x-coordinate here is negative 1. This becomes negative 5 minus a negative 5, which is plus a 5. It's 0, just as we expected, just like the rule told us. And now I want you to notice something else here. I won't answer it. I'm just going to pose you the question, and I want you to think about it. Look at this even function that we looked at. The integral, the antiderivative of our even function was this, which happens to be an odd function. Is that a coincidence? That the antiderivative of an even function is an odd function? That's my question to you. I want you to think about it. Over here, the antiderivative of an odd function was an even function. Now remember, for numbers, something is either an even number or an odd number for integers. But for functions, there are things that are neither even nor odd. So, is it a coincidence that in these cases, the antiderivative, or another way of saying this, is it always true that the antiderivative of an even or odd function is the other? If it's true, why is it true? If it's false, can you find an example that doesn't hold? Little challenge for you. Let me know if you have questions about that or want me to check over your answer. You can talk to me, send me an email, something like that. But that's the end of the video. That's even and odd functions. This rule can just make our lives a little easier sometimes. So that's why we introduce it. It'll come more into play later. And honestly, there was space for it in the first place in this section. Now, the next video is where I just do a bunch of problems, work on the homework, come to the selected homeworks problem video to see some examples if you're stuck, or if you just feel like you're completely lost and just want to see some more examples, that can work too. Best of luck and bye-bye.